Okay, welcome to your Chapter 7 introductory video. For this particular chapter, we're looking at what's called stoichiometry, and this is really the relationship between reactants and products, and reactants and reactants, and products and products. It's really kind of like a recipe. Similar to the way you can say to yourself, okay, if you know a given recipe and you want to make twice as many cupcakes, you can double the recipe. This is really what this chapter is about. The relationship between how much product you have, how much reactant you have and how much product you can form, and the relationships of all the ingredients. I'm going to cover most of the chapter. There's going to be a couple sections I'm going to eliminate um, and save for lecture, but beyond that, I think we will introduce most of the concepts. As far as coming away from this chapter with particular learning goals, you need to first and foremost be able to balance chemical equations. I don't stress this, so I keep it basic, and I just want you to get the fundamentals down because it's a skill that is needed for multiple things you'll do in Gen Chem 1 and 2. But the heart of this chapter is right here, and that is going to need to be able to master the interpretation of chemical reactions and carry out the necessary calculations. That is, how much product will form, how much reactant is needed, which reactant is limiting. These types of questions here can all be answered, and they all really take on the same approach. If you look at this as all individual questions and problems, you'll be overwhelmed if you start to see the relationship and realize, hey, really, it's the same thing every time. It's just a slightly different modification of that. You'll do much better. And then, of course, we're going to have empirical and molecular formulas. This is a major section of the chapter also. And then lastly, percent yield. So basically, these two are your major points in this chapter. And this is the outline. Like I said, I'll probably tackle most of this. I'll just introduce things like limiting reagents, really better called limiting reactants, um, and combustion analysis, empirical molecular formulas. Those are going to be advanced topics saved for class mostly. So let's take a look at a chemical equation. It's important here to realize what this notation is. And of course, we're learning this in lab already. This, of course, means it's a solid. This, of course, means it's aqueous, which means dissolved in water. That's what we mean when we say aqueous. This is a liquid, so it's not dissolved in water, it's just a liquid. In this case, it happens to be water, but we could have lots of different things that are liquids, and we've already defined this. You'll also see gas, and here's a liquid right here, H2SO4, so it's just a liquid substance. It's not dissolved in water. Now, what these reactions are basically are recipes, and what this is telling us is that one of these substances reacts with three of these substances to produce three of these substances and one of these substances. Okay, that is what these coefficients mean. Now, on a macro scale, if you're looking at a large scale reaction, it also translates to the number of moles. So it's the number of formula units, if you will, or in some cases molecules when it's a molecular compound, such as this. In other cases, you could think of it in terms of moles. It's just kind of like just scaling up a recipe. Okay, if it's 1 to 3 to 3 to 1 in terms of formula units, it's also 1 to 3 to 3 to 1 in terms of moles. It's just like using it a dozen. If the relationship is 1 to 3 to 3 to 1, it's also the same relationship as saying a dozen to 3 dozen to 3 dozen to 1 dozen. So the first thing you need to be able to do in any of this type of process of dealing with chemical reactions is to be able to balance the chemical reactions themselves. So you have to realize they follow this idea of conservation of mass. You have to understand that if I have a certain number of carbon atoms on the left side of the equation, that number of carbon atoms on the right side of the equation must be the same, because I'm not creating in chemical reactions any new carbon, and I'm not consuming up elements. Okay, I'm consuming reacting species. If you will, methane disappears. It no longer shows up on the product side, but carbon is still there, of course. The elements, it's kind of like building blocks. Like if you think about Legos or something, you're just pulling apart the pieces and reassembling them. So that's important to realize. So this particular reaction is methane plus ammonia gives us HCN, hydrogen cyanide, and H2 gas. Now it's not balanced as written here. So really, balancing is a three-step approach. And whether or not you use this approach or not that's up to you. I just want you to get basics down and start to feel comfortable. But the first thing you need to do is write the correct formulas for reactants and products, including the physical states. That is, in some cases, you're not going to be told what the products are. You're going to need to figure them out, and that comes with experience, of course. And if you're working on a reaction and let's say, okay, and you're told that hydrogen gas is produced, you have to realize hydrogen gas is H2, not H. Because if you write the wrong formula, you can't possibly balance it and get the right reaction. Okay? So that's critical, that you be able to write the equation based on what's told to you. And then this is just a suggestion. Balance an element that appears in only one reactant and product first. It just makes it easier if you do this. So if you will, don't start here with hydrogen because it appears here and here and here. It makes it more difficult. Start with carbon and then maybe move to nitrogen and then finish with hydrogen. That will help you in the process. And then choose coefficients to balance the other elements needed. So let's take a look. Right now, we have one carbon on the reactant side, one carbon on the product side. So effectively, that is balanced already to even start with. We have one nitrogen and one nitrogen. That's already balanced. Only the hydrogen has to be balanced. So we have 7 hydrogens on the left side because we got 4 and 3, so that's 7. And we only have 2 and 1 is 3 here. But if we take this and multiply it by 3, we now have 6 and 1 is 7, and then it will be balanced. So that's all you have to do here is add a 3 in front of the hydrogen. You do not change numbers down here, okay? You don't say, okay, we need 7 hydrogens, we need that. No, that's changing the actual chemical species, right? Hydrogen gas is H2. You can't change that number. Okay, so one of the main reactions you'll learn about in general chemistry is a combustion reaction. And one of the species that is readily combusts, as we know a lot about in terms of combustion reactions, are hydrocarbons. And hydrocarbons are molecular compounds composed only of hydrogen carbons. So exactly what the word says. Okay, and they are one class of organic compounds, and you know hydrocarbons. They're the fuels that you use, the propane for your stove, the gasoline for your car. Okay, the methane used to heat your home. These are all hydrocarbons. And when you combust hydrocarbons, of course, it reacts with oxygen in the air, and ultimately you're applying heat. And this little triangle means heat here. And the only products from a combustion reaction is CO2 and water. Now, that assumes it's a complete combustion reaction. That is, there's no side reactions, there's no problems. Well, unfortunately, that's not the case in your automobile engine. There's lots of side reactions. But for our purpose of our learning is that we're only going to focus on complete combustion reactions. Well, everything's converted to CO2 and water. And those are the only products. So this can easily be, balanced. And once again, we'll follow that rule. I'm going to start with carbon and say, okay, I've got one carbon and one carbon. I'm good to go. Then I'm going to move to hydrogen because hydrogen only occurs in 2 places. Oxygen occurs in 3 places. See? Oxygen, oxygen, oxygen. But you only have hydrogen, really, in 2 places. So let's start with hydrogen. And if you say to yourself, you got 4 hydrogen here, right? Then all we have to do is put a 2 out front. And now I have 4, and hydrogen's now balanced. Then you can go ahead and balance oxygen by basically putting the number here that is needed. And by looking here and you say to yourself, 2 oxygens, right? Now 2 times 2 is 4 oxygens. Now I simply need to throw a 2 out in front here and you'll wind up with 4 oxygens there and you'll be balanced. Now, of course, 2 critical processes that involve oxygen and carbon dioxide, which are major themes of this chapter, are photosynthesis and respiration. And all I want to say here really, these are the reverse of each other. And you should have learned this in basic biology. Photosynthesis takes the CO2 and water and converts it to carbon compounds and oxygen, and we do the opposite in respiration. We take the carbon compounds and oxygen and convert it to CO2 and water. So it makes a nice complete cycle. Now the heart of the chapter, the stoichiometric calculations. And once again, like I said, these are basically recipes. Okay? They're recipes that tell us what is going on between the reactants and the products. if you will, molar recipes. So, one thing you have to realize, two things that you'll always be able to use in solving these problems is the molar masses. And remember what that is grams per mole, and that's straight from the periodic table, and is equal to the AMUs. I mean, you figure it out the same way. It's different units. One is the mass of a formula unit. One is the mass of 1 mole. This is the mass of 1 mole, remember. But you just take them the same way from the periodic table. So, let me give an example here. Let's say that we know that there are 5 cups of flour plus, let's say, 3.5 cups of water, and that gives me 2 pizzas. Now, some of the type of questions you might be asked in this chapter is, hey, if you want to make 4 pizzas, how much flour do you need, assuming you've got as much water as you want? Well, I mean, you can all look at that and tell me 10 cups, but the way you would write it through dimensional analysis, when the numbers are hard and you can't see this, you're going to say 4 pizzas times 2 pizzas are produced for every 5 cups of flour. So effectively, that tells me how many cups of flour I need, right? It's going to be multiplying it by 2. This will be 2. 2 times 5 is equal to 10 cups. You can see that effectively. Or another way of looking at it is 5 cups gives me 2 pizzas. How many cups, if you like, kind of cross-multiplying if you're setting up ratios, do I need for 4 pizzas? It's really the same thing. As you can see, mathematically, you get the same answer. But this really is the heart of the chapter. And I can ask you other questions. I can also say, okay, well, if I want to make 6 pizzas, if I have 15 cups of flour, how many pizzas can I make, assuming I have unlimited amount of water? Or let's say I've got 15 cups of flour and only 3.5 cups of water. What's the limiting reactant here, and how many pieces can I make? Well, you can see that, right? You're going to have 10 cups of flour left over. This is what's limiting the water, and since 3.5 cups gives me 2 pizzas, you're only going to be able to make 2 pizzas, even though you have enough flour to make 6 pizzas. This really is, if you get this concept down, is the heart of this chapter in terms of stoichiometric calculations. Another thing I'm going to introduce here is percent composition. And I'm not going to spend much time on this because you've already done this in lab. But percent composition is defined as the composition of a compound expressed in terms of the percentage by mass of each element. So that's just the mass of the element in the compound times the mass of the compound times 100%. So a couple simple examples of that are right here. How much carbon is in methane and how much carbon is in C10H16 decane. So mass of carbon is 12, and there's only one of them, so that's all I have is up here. And then methane is going to be 12 plus the 4 for hydrogen, about 16. There you see it's 74.88%. So how much hydrogen is there? Well, you can do the calculation, or you can say, hey, there's only hydrogen and carbon, so therefore it must be 100 minus 74.88, and you can do it that way. For the next compound, same thing. You can figure out carbon. In this case, you got to do 12 times 10, because there's 10 carbons here, so you need this. And then the total mass once again, and you get your percentage. Okay, empirical formulas. Of course, our major topic in here, besides the stoichiometry, empirical formulas, it requires some stoichiometry. So what empirical formula is? The formula based on the lowest whole number ratio of its component elements. So for instance, if this substance here is what we call our molecular formula, the empirical formula would be this. Or if this is an empirical formula you figure out, it can be reduced to this. This is an ionic compound. This is always reported in its lowest ratio. So you're always going to have, just like sodium chloride. Just like calcium oxide, you could say it would be 2 to 2, actually 1 to 1. Calcium oxide would be Ca2O2, but you reduce that So it's that lowest formula ratio, if you will. And we can use that in a process known as combustion analysis. We'll come back to empirical formulas in the chapter, of course, in the lecture. Let's take a look now at this combustion analysis. And I'm just going to introduce how this is done. The percent of carbon and hydrogen in a hydrocarbon is determined from the mass of water and CO2 produced by combustion. And it's really quite simple. Realizing, in fact, that any carbon I collect, and that's what we're basically going to do, we have a CO2 absorber here. Any CO2 I collect here, the carbon in that had to have derived from here. It's the only place it can come from. Okay? So, obviously, if I can do some sort of stoichiometric calculation and relationship, I can back calculate, if I know how much CO2 I have, I can back calculate how much carbon was in the original sample. Also, in terms of water, the water that I'm going to collect had to derive, the hydrogen in that had to derive from here because there's nowhere else it can come from. So once again, I can use this type of stoichiometric calculation to back calculate and realize any of the hydrogen in water must have come from my hydrocarbon. That's really the essence of combustion analysis. So we're going to use this for organic compounds. And you'll see here, here's my sample going to be burned in the furnace. Here's my H2O and CO2 absorber. The carbon and hydrogen are converted to CO2 and water. Both are trapped, and the weight gain is measured. We can actually do other elements, and we'll touch on this in class. We'll actually do one in which there's oxygen in the original sample. It gets a little tricky, and the calculation's a little bit more involved. But we can come up with other traps and do other types of things to this analysis to figure out some of the other components if we have something other than a hydrocarbon and we just simply have an organic compound like a sugar or something like that that might have oxygen in it. One of the other major topics in this chapter I want to introduce is limiting reactant. I kind of talked about this already when I said, hey, if you have 15 cups of flour and only 3.5 cups of water, what's limiting and how many pizzas can you make? That is the essence of this entire section. You could look at these right here and realize that hydrogen is white and oxygen is red, and which one runs out first? And you might just want to say, okay, well, let me just count these up, and whichever one is less is the one that runs out first. Well, no, you can't do that. It might work in some cases. You might just get lucky. There's 1, 2, 3, 4, 5, 6 of these, and 1, 2, 3, 4, 5, 6 of these. These are the same. So how do you figure out which one is limiting? Well, you look at your recipe. We need twice as much hydrogen as we do oxygen in this reaction. There's my recipe, just like my flour and my water. So as a result of that, since we have equal amounts of them, we can say that hydrogen in this case is limiting. Because we really need, for 6 oxygen, we really need 12 hydrogen. So that one is limiting. So this substance will be completely consumed, obviously, just like my water would have been consumed and I would have been left with 10 cups of flour. Ultimately, it's the one that determines the amount of product that can be formed. We had said, it doesn't matter that I have 15 cups of flour. If I only have 3 cups of water, I can only make 2 pizzas. The last section in the chapter is percent yield, and this really is simply your actual yield divided by your theoretical yield times 100. What I want to do is actually define these. Your actual yield is what you get in the lab. It's the measured amount of the product formed that you actually get in the laboratory. That's what actual yield is. Theoretical yield comes from your reaction. That's my shorthand for reaction, Rxn. It's what you calculate from the stoichiometry. So it's what you calculate on paper, which is only going to be theoretical, because in the lab and in real life, you have side reactions, maybe you have contaminants that interfere with how much you actually produce. So it's rare you actually get an actual yield that equals your theoretical yield. So it's always going to be less than 100%. Okay, with that said, that is the end of the video, and be sure once again to watch this before coming to class.